Okay, this is how to draw the Lewis structure of the nitrate ion, NO3-. So the first thing you have to do, count the valence electrons. So the nitrogen has 5, each of these 3 oxygens has 6, so 5 plus 3 times 6 is 23. But now notice we've got to make an adjustment because our molecule is negatively charged. So we have to add 1 electron. So altogether we've got 24 valence electrons. Okay, so now next step, we've got to connect these atoms together using single bonds. And the more electronegative atoms tend to be on the periphery. So it makes sense to connect it with the nitrogen in the middle and the oxygens around the outside like this. So now we've used up 2, 4, 6 electrons so far. So we've got 18 more electrons to put on there. So we add those 18 electrons as lone pairs, starting with the electronegative atoms. So we can put 3 lone pairs there, and there, and there. So now we've used up all of our 24 valence electrons. And of course the overall molecule has a charge of -1. Now to finish off, we've got to check that our formal charges are as close to 0 as possible. So the formal charge, we'll do the nitrogen first. The formal charge on that nitrogen is its valency, 5, minus the number of electrons that belong to it in this structure, which is 1, 2, 3. So the formal charge on the nitrogen is +2 in this structure. Now we'll look at the oxygens. They're all the same, so we'll just look at one of them. The formal charge is the valency, which is 6, minus the number of electrons belonging to it in this structure, which is 1, 2, 3, 4, 5, 6, 7. So the formal charge on all the oxygens is -1. So we can adjust this structure in order to get these numbers closer to 0. So we can do it by moving one of the lone pairs from one of the oxygens in to make a double bond. So I'm going to redraw the structure now. I'll draw it over here. So we've got the nitrogen, that's now a double bond to the oxygen. Now there's only 2 lone pairs up there. And the other atoms are unchanged. So let's see if this is an improvement. So the formal charge on the nitrogen is now its valency, which is 5, minus the number of electrons that belong to it, which is 1, 2, 3, 4. So the valency on nitrogen is now +1. And the valence on this oxygen up here is, the formal charge on this oxygen here is its valency, 6, minus 1, 2, 3, 4, 5, 6, which is 0. So that atom there has a formal charge of 0, and these two here still have a formal charge of -1. So that's as good as we can go. We can't make another double bond here because the nitrogen can't have more than 4 bonds. So that's as far as we can go. But this is still an improvement compared to over here, because in the previous example, the nitrogen formal charge +2, and each of these had formal charge of -1. Whereas down here we've got nitrogen has a formal charge of +1, it's closer to 0 than before. One of them's made it to 0 and the other 2 are unchanged. So we've still had an improvement compared to before. So this is the final Lewis structure. But up here, when I chose which oxygen to move a lone pair, I just arbitrarily chose this first oxygen. It would be just as valid for me to choose this oxygen or this oxygen. So let's see what happens if instead of doing that one, I did this one. If I'd done that, I would have got this structure. And that structure there would be equally valid. Also, I could have done it from this oxygen. I could have moved one of these lone pairs in, and that would have given me this. And that would be another equally valid way of drawing the Lewis structure here. So this is an important concept in chemistry. If there is more than one way to minimize the formal charges, then none of these individual Lewis structures by itself is an accurate description of the true structure of NO3-. The true structure of NO3- is best represented by an average of these 3 Lewis structures. And the way that we represent that in chemistry is we put these little double-headed arrows to indicate that actually none of these individual structures are a good representation, but as an average, if you average out these 3 structures, then you will get a good representation of the true structure of NO3-. So let's look, and this concept is called resonance. When you need to average out different Lewis structures in order to get to the true structure, that's called resonance. Now, let's look at that a little bit more closely. Let's consider this NO bond here. So in this particular Lewis structure, it's a double bond. In this structure here, it's a single bond. In this structure here, it's a single bond. So when we average them out, the bond is going to be neither a true double bond nor a true single bond. It's going to be somewhere in between, where it's going to have some double bond character and some single bond character. So the bond length of the nitrogen-oxygen is going to be somewhere in between a double bond and a single bond. And all three NO bonds in this molecule are going to be of the same length, and they're all going to be intermediate between a double bond length and a single bond length. So that's the Lewis structure of NO3 minus. You actually need to draw three structures like this.